Greetings everyone. Today we're going to explore multiplying radicals. You might have a radicals foldable, and if you don't, just make sure to jot these down in your notebook. Here's the tab we're looking at today if you do have this foldable. Let's get started. Let's talk about multiplying radicals. Now, before you write anything down, let's talk about what you do know. We've worked on multiplying variables. When we multiply variables, it actually means we have four pieces that are being multiplied here. We multiply the 2 times the 3, and we multiply the x times the x, which gets us to x squared. So we can multiply anything and everything. And so we want to see how this plays out with radicals. So up at the top, let's jot down a few notes. First, we can multiply radicals if they have the same index, meaning I can't take a square root times a cubed root. First, if you want to think of these as steps, you're going to multiply the numbers that are outside the radical, and you're going to multiply the numbers that are under the radicals. And then you might have to simplify, right? If I'm multiplying values, I'm going to have bigger numbers, which means I might have to simplify the radical. Let's jump into the examples. Remember, pause at any time. Example 1. Technically, I have 1's outside. So I could write a 1 outside, but let's just worry about the radicands. If I multiply a 3 times a 3, I have a radical 9. See how it stays under the radical? But what is the square root of 9? The square root of 9 is just 3. It's a perfect square. We don't need to simplify or show anything else. It's just 3. Let's take a look at example 2. I have 2 radicands, and if I multiply them, I have the square root of 20. Well, that simplifies. What's a perfect square that fits into 20? 4 and 5. The square root of 4 is 2, and square root of 5 does not simplify. I have 2 radicands. 12 times 4 is square root of 48. Well, that definitely needs to reduce. Let's talk about a perfect square that fits into 48. Now there's a couple of them, but we want the largest perfect square. The largest perfect square that divides into 48 nicely is 16. The square root of 16 is 4. And the 3, I like to call them the bad roots. They stay in radical jail. Let's look at our next set. Technically, I have a 1 out front. A 1 times a 2 is a 2. A 2 times an 18 is going to create my radicand, which is 36. So the 2 falls down. What is the square root of 36? It's just 6. Now these are next to each other, so what operation does that imply? Multiplication. Our final answer is just 12. Let's look at the next one. 2 times 4 gets me a value of 8. 12 times 15. Oh my goodness, let's see, that's 180. So the 8 just hangs out, but we definitely need to break apart that 180. We want the largest perfect square that fits into 180. It might take some guessing or checking, but 36 fits in 5 times. The 8 falls down. Square root of 36 is 6, and the square root of 5 falls down. When numbers are written out front, it implies multiplication, so our final answer is 48 square root of 5. This next one, we're going to treat it like every other value that's in front of parentheses, and we are going to distribute. 2 times 2 is 4. 2 times square root of 3. Well, there's a number on the outside and there's a number on the inside. So it's going to be 2 radical 3. Now, if there was a plus sign to begin with, it remains a plus sign. Can I add a radical and a non-radical? I can't. So in this case, that's my answer. We've got 3 more to go. I separated these out for space, so just be aware of how much space you might have in front of you. We're going to distribute again. Square root of 3 times 3. Well, there's an outside number and an inside number. We want to write the outside number out front so it doesn't get confusing. Let's multiply again. Square root of 3 times square root of 6. They're both radicands, so they get multiplied and they stay underneath. 6 times 3 gets me to 18. That plus sign is still hanging out. Let's talk about the 18. It breaks apart. Square root of 18, the perfect square that fits in is 9. Square root of 9 is 3. And let's drop down this 3 radical 3. Can I add these? I can't. They have different radicands. They are unlike radicals. Therefore, that is my final simplification. Let's take a look at this next one. We have 2 pieces times 2 pieces, which means some of you have used the box method, some of you have used the acronym FOIL, some of you have just double distributed. I'm going to show double distribution. If you want to try it another way, please do so. What that means is I'm going to distribute the 3 twice. So 3 times 3, that's going to be 9. 3 times negative 4 square root of 3. Well, it's going to be a negative. 3 times 4 is 12, and the radical stays. See how that happens? That came from 3 times negative 4 square root of 3. So we could only multiply the numbers out front. Okay? All right. Now I need to do my next distribution. I need to take square root of 3 and distribute it twice. Square root of 3 times 3. Well, that would just be a positive 3 with a square root of 3. There's nothing we can do about it. Square root of 3 times negative 4 square root of 3. Let's talk about that. It's a negative 4 out front. The 3 radicand times the 3 radicand gets me a 9 radicand. See how we went to 4 pieces? That should happen if we're showing all our work. Now let's simplify some things. I'm going to deal with this right side. Square root of 9 is 3, and 4 times 3 is negative 12. See how I got that? Let's deal with the middle. Hey, these are like radicals. If I have negative 12 of them and 3 of them, I have negative 9 of them. See how that worked out? And I'm just going to drop this 9 down. I haven't used it yet. Hey, I have one more step to go. I see that I have just regular old numbers. 9 minus 12 is negative 3. And the negative 9 radical 3, I didn't use it, so it falls down. Now, I cannot subtract these. This and this are not like values, so we cannot combine them any further, which means that is my simplified value. All right, let's try this last one. We want to double distribute again. I'm going to try to use very specific colors. First, I'm going to distribute the 2 times radical 3. Well, those are unlike, so I'm just going to write them next to each other. Then let's take 2 times negative square root of 6. Well, I can't actually multiply the 2 and the 6. One's an integer and one's a radicand, so negative 2 square root of 6. Let's keep going. Now I have to distribute square root of 3. Square root of 3 times square root of 3. They're both positive. 3 times 3 is a radicand of 9. Square root of 3 times negative square root of 6. A positive times a negative is a negative. A radicand of 3 times a radicand of 6 is a radicand 18. If you need to, pause, rewatch that part. Let's simplify. The 2 radical 3 does not reduce. The negative 2 square root of 6 does not reduce. Square root of 9 does. Square root of 9 is just a regular old 3. Square root of 18 reduces. We're going to have square root of 9 times square root of 2. Square root of 9 is 3. Square root of 2 remains. Look at, these are all unlike. The 3 can't combine with the 6 or the 2. They're all unlike radicands. So believe it or not, that is all we can do. It's long, but we eliminated parentheses and reduced our radicals. Alrighty, I know that's a lot to consider. Please, I encourage you, if you were taking notes while watching this video, re-listen to it or re-watch it without writing, right? It's kind of like a movie. If you just watch it without doing anything else, you'll remember it better. As always, make sure to check out Google Classroom to see what the task is to go along with this topic. Let me know if you have questions. Seek out the CUDA webpage if you're looking for more practice. You can find a whole section on operations of radicals. Let me know what you need, and until next time, have a good one.